Hello, welcome to Tech Dicted, and previously we talked about the SR. We started with the SR latch, proceeded to the SR flip-flop, and now we are looking at the JK flip-flop. So as you will notice, and even as we proceed forward, you will notice that you keep on adding things to the circuit, but it's the same exact circuit, just that we're increasing maybe the clock and gates. For example, here to here we just added this part, here to here we just added this last part. The JK, S and R are in the inner side. Okay, so we have our SR. Then now the whole thing is now the JK flip-flop, and that's where what we are looking at today. Now the JK flip-flop works exactly the same way as the SR flip-flop, but in the instance where both are 1-1, there is a toggle. Okay, we toggle. If it was 0-1 at the output, then it will be 1-0 at the output. Let me just demonstrate that. Now let me just go to a clean sheet. Okay, that's our sheet for the day. Place this here, and then let's just write this down. So when we have a 1-1, okay, this is an AND gate. So let's assume our output is 0-1. We always need an output on this case. So let's assume our current outputs, okay, these are our current outputs. This is 0 and this is 1, okay, and then our input is 1-1 because that's the state we are in. So there is Q, there is J, K, Q, and Q naught. Now our inputs are 1-1, our current outputs are this, so we are looking for the other outputs. So when we have a 1 and a 1, so the clock must be high for this circuit to work, just like the SR flip-flop. The clock must be high. When it's low, then the state, what is in memory, is maintained. So when the clock is high, this is 1 and this is 1. Then we have this at the output. Remember, this is an AND gate. NAND gate. And in the NAND gate, this is our truth table, just as we looked at in the previous two sessions we've had. So now we will use that. Let me just hold it there. So we have our J input as 1. Okay, so we are looking at the inputs at J. We have our J input as 1. We have our clock input as 1. And then at the output of Q naught, we have a 1. So that means 1, 1, 1. If it were an AND gate, it would be 1. But since it's a NOR, then it's not AND, so it's a 0. Okay? It's a not AND. So whatever AND is, we do its complement. So therefore, we have a 0, and the output here will be 0. Okay? Output, when the output is 0 in a NAND gate, okay, 0, when the output is 0, so we have a 0, we have a 0, we have a 0, and always the output will be 1 when the input is 0. So therefore, we don't even need to know what this other input is. We don't need to know it. We just have here as a 1. Okay? Then let's look at the K side of things. So since we have here as a 1, let's look at the K side of things. At the K side, our input is, first of all, we have the clock as high. Then we have the K input as high because K is 1 right now. And then we have Q, which is the output, as 0. So with this, then we know that 1, 1, 0, therefore, this would be 0 if it were an AND gate, and this way. But since it's NAND, then our output is 1. Okay, this is for the NAND because it's not what is AND. So it's the complement of AND. Okay, so we have 1 as our output. Okay, let me just do this. You see, it's 1 as our output. Therefore, this output, okay, 1, 1, 0, 1 is our output here. For the NAND, we're not so sure. When we have a 1, we're not so sure because it can either be a 1 or a 0. Okay, but then we are here. So we want this input. This input is now 1. Okay, so we take the Q input. So since we have a 1, but it cannot tell us anything further, we have a 1. Let me just write it here. We have a 1 at this input, but it cannot tell us much. Okay, a 1 at this input does not tell us much because, as we've seen, the output will either be a 1 or a 0. So therefore we need this other input, which is a 1. Okay, Q is a 1 as of this moment, and therefore since Q is a 1 and this is a 1, when we look at this 1 1, we have a 0. So the output here will be 0 and Q naught will be 0. So from what we have looked at previously, let me just put this back up so that we don't have a lot going on. So from what we've looked at previously, then we note that in this last state, when we have an AND gate, I don't know where I have my, this one. In this last state, when we have 1 1, then we toggle. Instead, from the previous time, when we were looking at the SR, we did not toggle, but rather it was an invalid state because we would not know what was what. But since the inputs are now going back, okay, to the J and K, so it's like we have 3 inputs. Since we have these 3 inputs, that's what makes the difference between the 1 1 state at the SR latch or SR flip-flop and the JK flip-flop. In the JK flip-flop, we have an easier time because this is no longer an invalid state. It's a state that toggles. Okay, so in this one, we have the first one. Okay, when both are 0, it's exactly the same as for the SR. Exactly the same as for the SR flip-flop. These 3 states. When both are 0, we're saving what's in memory. When 0 1, we reset. 1 0, we set. Then 1 1, that's where the toggle action is, instead of just having an invalid state, which leads to an unknown state after that invalid state, as we looked at in the timing diagram for the SR flip-flop. Yeah, so that's what we have. Now let's just look at one last thing. It's nothing major. This is our symbol for the SR, for the JK flip-flop, sorry. So we have our J input, K input, clock, Q and Q naught. And that's our symbol, and that's it for today. Thank you.